Hi, this is Ms. Fitzmaurice. This video is about center of mass. So by the end of this video, you should know what center of mass is, you should know how to calculate center of mass, and you should be able to explain why it is useful. Alright, so I'm going to start with some basic examples. Now, center of mass is exactly what you expect it to be. It's kind of the middle of an object if you balanced out where all the weight is. Okay, so for like a meter stick, it would be right in the center here. For a circle, it would be right in the center. Slightly more complicated, if we had a pickup truck, and this is my beautiful version of a pickup truck, most of the weight is located kind of towards the bottom of the truck, and we can probably guess it's going to be towards the front cabin because there's more stuff up here in the front. It's not going to be located in the back, so I'm going to erase that dot because there's not as much stuff in the back. Okay, so that's the basic idea. It's like if you were to put a point on the average place of the mass, where would it be? Okay, but that's a little bit vague, and it's easy to see for, a sphere or a meter stick, but we need a more formal mathematical definition. And so the formal mathematical definition is that XCM, and that's our center of mass, or the position for our center of mass, is equal to the sum of all of the parts of a system. Okay, so hopefully you've seen sigma I in math. So if I had 5 different objects, if I added up their position times their mass, and I divided by their position. Now, this maybe looks a little bit scary and complicated, but the bottom is just our total mass. If I add up all the mass, and the top is kind of like helping us find a weighted average of where the mass is located. Alright, so here's my example. And center of mass, because it's a position, we always need to pick where a zero line is. So let's say we have this picture. We have basically a meter stick with, let's say, some red Play-Doh stuck to the end. The meter stick has a length L, a mass M, and the Play-Doh has mass 2M. It's really heavy Play-Doh. And so if I want to know the center of mass, okay, you can probably guess, and I'll say this is my x equals 0, because I always have to pick an x equals 0. You're probably going to guess that it's closer, okay, to the blob of Play-Doh at the end, and it's going to be not located towards the end without the blob of Play-Doh, because it's center of mass is basically like an average place of where your mass is. And we can use our equation. We have XCM is equal to sigma x I m I divided by sigma m I. Okay, the denominator, again, this is just all the mass added up. So in this situation, I have m plus 2m, and in my denominator, I have 3m. Now, on the top, I have x. I'm going to name my objects. I'm going to say the meter stick is object A, and my blob of Play-Doh is object B, so I have xb mb plus xa ma. Okay, remember the meter stick is A and the blob of Play-Doh is B. And so I can do this calculation. I know the center of mass will be 1 over 3m times all of this stuff in the numerator. So I have xb, okay, and I know that the Play-Doh compared to my axis is located at x equals L, okay, because it's the whole length away. So I have L. My MB is going to be 2M. Okay, I already know the meter stick is, its center of mass is going to be in the middle, okay, kind of where you would feel its weight, and that's at L over 2, so I have L over 2 times the meter stick's mass, which is just M. And so I have an M in every term at the top and an M in the bottom. My M's go away, and I have 1/3 2L plus L over 2 which ends up being 5 over 2 times 1 over 2 L, which is 5/4 L. And if we back up 1 second, I just realized I made a mistake. I took this 3 and I somehow made it into a 2. So we have 1 over 3, and I actually don't have 5/4, I have 5/6. So that kind of matches my prediction. I expected my center of mass, my center of gravity, to be closer to the Play-Doh and further away from the empty part of the stick. Alright, so here's another example, and I actually want you to pause this video and try to do this by yourself. Okay, so I have 3 blobs connected together by a stick that doesn't weigh very much. So we have 2 blobs that each have a mass of m. They're separated by a distance of L over 3, and the second little m and 4m are separated by 2L over 3. And I want you to try to find the center of mass of this object. Okay, so go ahead, try to do that by yourself, and then unpause the video and try to get the answer. Okay, so now that you have tried that, we're going to calculate the center of mass. And remember that xcm is equal to adding up over all of our objects, the mass of our object times the position of our object, divided by our total mass. Okay, so we have xcm equals, and we know here our total mass is m plus 4m, which is 6m. And then I'm going to name my masses A, B, and C. So I'm just going to write that out first. MA XA plus MB XB plus MC XC. And I know that XA is 0, because A is just sitting on my x equals 0 line. For xb, I'm going to put L over 3, and for xc, L over 3 plus 2L over 3 is L. Okay, so I'm going to go ahead and continue to plug things in. I have m times 0 plus m times L over 3 plus 4m, because MC is big, times its distance, which is just L, all over 6m. And notice I have an m in every single thing, so I have my m's canceling out. And that makes sense because L is a length and we want xm, our center of mass, which is a distance or a position, to be in meters or length as well. So we have xcm is equal to, I'm going to bring the 1/6 out, L over 3 plus L. Okay, that means that xcm is equal to 1/6 times 4L over 3. Okay, and we can cross this out and get a 3 and a 2, and we have xcm is equal to 2L over 9. Alright, so hopefully that doesn't seem too bad. The next question is, what if our shape is 2D? So let's say that this is a top view of a little merry-go-round on a playground, and we have 4 kids. These black dots are our 4 kids sitting on the merry-go-round, and the whole merry-go-round has a mass of 2m. What should we do? First of all, we have to pick out a 0 line. But because we're dealing with a 2-dimensional shape, we need both an x0 and a y0. So I'm going to pick the very center of this shape to be x equals 0 and xy equals 0. I should say xx and xy are both 0. Now, what about the equation? We just had a 1-dimensional equation. Hopefully, if you remember back to the beginning of the year, you can remember that basically everything we could do in 1 dimension, we could do in 2 dimensions. So, if you wanted xxcm, okay, the side-to-side center of mass, you could also find xycm, the up and down center of mass, and then your actual center of mass would be a set of coordinates xx, xy. Okay, so just like the normal center of mass formula, xx center of mass will be the sum of all of the x positions of our objects times the mass of our objects divided by the sum of the total mass, and xycm will be the sum of all the up and down coordinates for every single mass. And these little i's just say I'm adding up mass A plus mass B plus mass C. Okay, so I want you to pause this and once again try to find the center of mass for this object, and then check back in for the answer. And actually, before I say that, we need to establish the radius of this disk or merry-go-round is r. Alright, so hopefully by now you've given this a try. What I'm going to say is I think it's much easier to do this if you first establish what the coordinates, and the coordinates are going to be xx, xy, are for each object. Okay, so for our first mass right here, at the bottom, okay, it's, if I kind of draw this orange line is representing my like plus x, and this is plus y. So the coordinates of this bottom mass will be nothing in the x direction, and in the y direction it's at a position of negative r, okay, with respect to this 0. Now my second mass, right here, it has an x position of positive r and a y position of 0. The top mass has a x position of 0 and a y position of positive r, and then this fourth mass has a x position of negative r and a y position of 0. Okay, so what I'm going to do is I'm going to plug our masses and our objects into the two equations I just showed you. Okay, lastly, I need to not forget that if this merry-go-round is truly circular, it has a center of mass at 0, 0. Okay, so I'm going to first find xcm, and I know that's going to be the sum of all the x positions times the masses of all my objects divided by the total mass of all my objects. Okay, so all of my objects, I have one fat kid, 3m over 2, plus m, plus m, plus m, plus the merry-go-round, which has a mass of 2m. And then in terms of x positions, and notice I'm only looking at the x positions, only these two objects, I'm going to name all of my objects, A, B, C, D, and let's call the merry-go-round E. None of the objects except for A and C have non-zero values for x positions. Okay, so I'm just going to put those two in. And for MA, I have M, because that's the mass, times negative r. Okay, and for MB, or MC, I have M, because that's the mass, times r. And what we realize is that m times negative r plus m times r is actually equal to 0. So our total x center of mass is at 0. And that kind of makes sense because if you were to look at like how balanced this thing would be left-right, it would kind of balance out in the middle. So I have xxcm equals 0. Now in the y direction, xy center of mass, that's going to be the sum of all of the positions in the y direction times the masses divided by the total masses. Okay, the total amount of mass is going to be the same. So I'm going to take a second and just add up everything in this green circle. And I know I have 3m's plus 2m, which is 5m, okay, which is 10m over 2, plus 3m over 2 is 13m over 2. Okay, so my total mass is 13m over 2. And I'm going to take that and I'm going to put it directly in here. So I have xycm equals some stuff times 13, or divided by 13 over 2m. Okay, and I only need to worry about the objects that have a non-zero y value for their position. So that's the ones I'm outlining in blue. And there are only two of them. Okay, so I have their objects B and D. For object B, its mass is 3m over 2. Okay, its distance is r. And for D, I have plus m times negative r. Okay, so hopefully you look at this and you realize that when I add 3m over 2 plus m times negative r, I end up with m over 2r. Okay, you also notice that I have an m in every term, so the m's go away, so I have xycm equals 1 over 2 r divided by 13 over 2. Okay, these 2's will cancel out, and what I end up with is xycm is equal to r divided by 13. Okay, so the coordinates for the center of mass would be 0, comma, r over 13. Alright, so hopefully this procedure doesn't seem too bad, but it does take, a lot of filling in formulas and a lot of fractions, so why is this useful? The reason why this is useful is that all of the equations we've ever used, so sigma f equals ma, okay, all of our kinematics equations, all of our conservation of energy equations, sigma E naught equals sigma E, sigma P naught equals sigma P, all equations that don't deal with rotation, okay, that are translational, are true for the center of mass of an object. And that includes any object that's being deformed. Okay, so if you were to jump off of the floor, probably you start out with your knees bent, okay, and then you jump off, and this is the floor, and you jump up to a certain height, and then you come back down, and you land with your knees bent. Physics still applies to you, even though you are personally changing shape, as long as instead of keeping track of like the top of your head, we keep track of the center of your mass at all times.